for the invitation, for possibility to listen with interesting talk, and for possibility to give a talk. Also, I thank Professor Kaufman for interesting discussions, for his idea, conversation, and happy birthday. Today I will speak about some results which we have found with Tatiana Kozlovskaya. Tatiana Kozlovskaya is professor of Tomsk Tomsk University, and my talk is dedicated some result which connect with multi-virtual braid groups and their representation. At first, I recall some general thing about connection of knot theory and braid theory. In the classical case, these connections is the following. On one side, we have a set of braid group B1, B2, and so on. And on the other side, we have classical load theory. We know that we can construct geometric interpretation of braids, and from any braid, we can define some link or not. On the other side, we know the Alexander theorem that with map its epimorphism, and any link we can present as a closure of some braid. Also, the main problem of the classical knot theory, which is classification of knot, we can reformulate in the terms of some purely algebraic problem for braid group. For example, conjugacy problem, stabilization, and destabilization maps. And Professor Kaufman in 1996 constructed a generalization of knot theory, and he defined the virtual knots. And also now we know connection, the similar connection for virtual braid groups, VBN, with groups was were defined by Professor Kaufman, and he defined a virtual nodes. And also we know some analog of Alexander theorem and the Markov theorem. Markov theorem was proved by Seichi Kamada and later independently Kaufman and Labrampoulos. And from this time, a lot of people study the virtual knot theory, virtual braid group, and connection between them. And then in the last year, Professor Kaufman put in archive the preprint with title multi-virtual knot theory. This is very long preprint, 82 pages, where he introduced multi-virtual knot theory and multiple virtual braid groups, and he find connection between them and prove some analog of Markov theorem. I divide my talk on 5 parts. In the first part, I recall the definition of a multiple virtual braid group and a symmetrical multiple virtual braid group. This group was suggested in the preprint of Kaufman, and in the second part I defined multiple virtual pure and semi-pure braid group. In the third part, we discussed representation of multiple virtual braid group, and the fourth part I explained how it's possible to define knot invariant using different type of representation. And in the last part, I, I will give answer on some question of Professor Kaufman. First part, multiple virtual and symmetric multiple virtual braid groups. The definition is the following. Suppose that K be a non-negative integer. When K virtual braid group, K MVBN presented by Kaufman last year, and this group as combinatorial objects and can be defined by the set of generators sigma I. This is the classical Braid generators, and C rho I with index alpha. Alpha goes from 0 to k minus 1. In this case, we have k different type of virtual crossings. This is the set of generators, and the set of relations are now it's geometric interpretation. We have geometric interpretations, its diagram on the plane, geometric interpretation of the generators. This is the sigma I, and here we have virtual generators rho I with index alpha, and near the crossing we will write alpha because we have a different type of virtual crossings. This is the set of generators, and now the set of relations. We have some types of relations. The first relations is involutivity of generators. Rho I alpha in the square is equal to 1. But of course, sigma I has infinite order. And uh, second part of relations, this is the so-called commutativity relations. Uh, the first relations, I call them homogeneous commutativity. Homogeneous means that we consider the generators from one family. See, we have commutativity for the sigma I, sigma j, and we have commutativity for all virtual crossing from one set. And also we have mixed commutativity. If alpha is not equal to beta, then we have commutativity of sigma I, rho j, and commutativity for rho I and beta j with different indexes, alpha and beta. This is commutativity relations and Braid relations. For Braid relations, we also have homogeneous relations in for generator sigma I, the similar relations for the virtual generators, and now we have a mixed Braid relations. It connects sigma y and rho I plus 1 rho I with index 0. You can see that we have two generators rho with one index 0. And now we have a similar type of relation where two generators with index 0 and one with index beta. Uh, we can give interpretation of these defining relations in the as a data move. You can go from Braid to correspondence node and see we have data move for the condition if all crossing has index 0. And in this case, we have so-called forbidden relations, and forbidden relations are the following type. The first forbidden relations, it's virtual not fairy. If we have two generators sigma I and one generator rho I, these relations, it's forbidden, and the relation symmetric relation with two elements sigma I, and also we have forbidden relations which contains different type of virtual generators rho 0, rho beta, rho gamma, and rho beta. In the case when k is equal to 0, our group KMVBN is the classical Braid group BN. And in the case K equal 1, our group is the virtual Braid group VBN. Also, on this picture, you can see the forbidden data move if alpha is bigger than 0, then we can use this data move of this type. Also, Kaufman suggested to study some analog of this group in which are allowed data move for any types of virtual crossings. The definition is the following. Let k is more or equal to when symmetric multiply k virtual braid group. I will write k mvbn with tilde is a group which is quotient of KMVBN by the forbidden relations F3. Hence, we have data move for all virtual crossings. But in this theory, also the following relations are forbidden. It's the same relation which we have, the same forbidden relations which we have in the virtual knot theory. This is the definition, and now I recall some fact from the classical knot theory and virtual knot theory. I recall that the braid group Bn is a group with the generator sigma 1, sigma n minus 1, and with defining relation of the braid relations and the commutativity relation. To study this group, we construct an epimorphism Phi from Bn onto symmetry group sigma n. Generator sigma I goes to the transactions I and I plus 1. The kernel of this epimorphism is called the pure braid group and is denoted by Pn. And Markov proved that Pn is the semi-direct product of the three groups. Pn is the semi-direct product un minus 1, and so on, u2, where uk is the free group of rank k minus 1. Hence, we have the structure of the group Bn. We can solve the word problem and so on. And now I recall the definition of virtual braid group in the case of k equal 1, when our group is isomorphic to virtual braid group VBN, which was introduced by Professor Kaufman, and this group is generated by the classical braid group Bn and the symmetry group sigma n with the generators rho 1, rho n minus 1 where the generators rho I satisfy the following relations with relation for the symmetry group. Also we have relations for Bn and we have the mixed defining relation. Have a look. We have for commutativity relations, mixed for commutativity relations, and we have a mixed relation where two generators rho and only one generator sigma. And also Professor Kaufman and Professor Lambropoulos defined some quotient of VBN. In particular, they study flat virtual braid group, welded virtual braid group, unrestricted, and so on. But for us, more interesting the so-called flat virtual braid group. I recall that this group is denoted by FVBN and is the quotient of VBN by the relations. Sigma I square is equal to 1. Hence, a flat virtual braid group of VBN is generated by two symmetric groups. But of course, the structure of this group is more complicated. And we know definition of virtual braid group. For definition, we must construct epimorphism Phi from VBN onto symmetric group Sn, in which sigma I goes to rho I, and rho I also goes to rho I. The kernel of this map is the pure braid group. It's not difficult to see that following elements alpha I plus 1, see it's the product rho I and sigma I inverse, and its conjugation sigma y minus 1 rho I, and conjugation with all these elements lies in the pure braid group. And In fact, this set is the set of generators for VPN, and it's possible to prove the following theorem that the VPN uh, can be generated by this element lambda ij and the following set of defining relations. You can see that the first relations it's a commutativity relation, and the second relations it's look like and Young-Baxter relation. But in this case, we can construct not one epimorphism on the symmetric group, but also it's possible to construct another type of epimorphism. Rabenda defined the following epimorphism of VBN on the symmetric group Sn, in which sigma I generator goes to 1 and rho I goes to rho I. We will call this the kernel of this epimorphism by semi-pure virtual braid group and will be denoted it by Hn. Rabenda proved that Hn is generated by the following elements xij, where you can see that xij plus 1 is sigma I, which is in the kernel. And now we consider the conjugation by this element, and we defined the elements x with indices ij and the indices ji. With set from the kernel, and Rabenda proved that Hn can be defined by the relations of two types. The first relation is commutativity relations, and the second relation, you can see that the second relations contain only two generators, and we see that Hn is the Artin braid group. And Rabenda proved the similar result that we have for pure braid group that VBN it's the semi-direct product of HN and the SN, and symmetric group SN acts on the generators Xij as permutation of the indices. Hence, we have some decomposition of virtual braid group. And now let us define the multi-virtual pure and semi-pure braid group. For simplicity, we shall denote rho I with 0, because you see that these generators more important for us. And we know that the group which is generated by rho 1, rho n minus 1 is isomorphic to symmetry group Sn, and we can define a map on the generators, the map phi and k from multiple virtual braid group into symmetry group, under which all sigma I goes to rho I, and all rho I with index alpha goes to rho I. This map defines an epimorphism, and in kernel it's called the multiple pure virtual braid group. I will denote it KMVPN. Also, we can define another map which is similar for the map of Rabenda. We can define the map C and K from multiple virtual braid group to symmetry group, under which the generator sigma I goes to 1, and all generators rho I alpha goes to rho I alpha goes to rho I. This map induces the epimorphism, and its kernel it's called by multiple semi-pure virtual braid group. And of course, it's interesting to find the set of generators and defining relations for this group. Let us define the elements of the following form. Lambda I plus 1 with index 0, it's the same as we have for virtual braid group, its element rho I sigma y inverse, lambda I plus 1 y its element sigma I inverse rho I, and we have lambda I plus 1 beta, it's the product rho I and rho I beta. But see, now we have only elements lambda I plus 1 beta, but we don't have lambda I plus 1 I. And also we define the similar elements lambda ij with 0, lambda ji with 0, and lambda ij with beta, but we don't have lambda gi with beta. With some set of elements, and it's not difficult to see that all these elements live in the kernel of the map phi and k. Oh, sorry. And we prove the following theorem that the group multiple virtual pure braid group can be generated by element of the form lambda ij with index alpha, lambda ji 0, and it's defined by the following set of relations. You can see that this is commutativity relations, this relation which look like as Young-Baxter relation, and this relation is as Artin relation. We have presentation for this group, and now we can found some properties of the group KMVBN. The properties are the following: that KMVBN it's the semi-direct product of the pure group and the symmetric group Sn, and the actions it's the same acts as permutation of the indexes. If we consider the generators lambda ij with index 0, then this group it's isomorphic to VPN, the virtual pure braid group. On the other side, for any lambda from the set 1 to k minus 1, if we consider the group with these generators, then this group is isomorphic to the flat virtual pure braid group. And in the case n equal 3, we have the following decomposition as free product, virtual braid group, and now we have some copies of flat virtual braid group with free strands. And also, we can find the similar results for group KMVHN. Also, we can define this set of generators, and we can find the set of relations. We proved the following theorem. Now we have a set of generators and set of relations for both these groups. And now I am going to representation of multiple virtual braid group. At first, I recall the results from the classical braid theory. I recall that the Artin representation, we will denote it phi A, it's the map from braid group Bn into the group of automorphism of free group Fn. Here, free group Fn, it's a group with generators x1, x2, xn, and so on. And any generator sigma I goes to the automorphism of the following form. Xi goes to these elements, its conjugation of xi plus 1. Xi plus 1 goes to xi, and all our generators are fixed. This is very good representation because this representation is faithful, approved of Artin in 1925. And it's interesting to construct some representations for virtual braid group. The first type, the first this representation constructed Vladimir Vershinin. This is representation phi with index v, and you can see that it's x on the generates sigma I as Artin representation, and the image is rho I. It's only permutation of generators. But of course, this representation is not has no trivial kernel because this is the so-called welded braid group, and welded braid group is the quotient of VBN by some forbidden move. Also, Professor Manturov constructed the representation of the following form, where we consider the map from VBN into automorphism of Fn plus 1. Here Fn plus 1 is the free group with one more generators, and the action is the following. Here it's the map as a Artin representation, and now rho I goes to automorphism of the following form. Xi plus 1 goes to conjugation y minus 1, and xi plus 1 goes to xi and conjugated by y. In this case, we don't have forbidden relation. And also there are some other construction of representation, for example, Silver and William constructed representation of VBN into the group of old Fn and plus 1, which is a free product. Fn it's a free group, and Zn in the power n plus 1 it's free abelian group with these generators, and the action you can see here are the following. Also, the for 6 alpha, Boden, Diaz, and so on, constructed a representation of VBN into automorphism Fn2. And in our paper with Yulia Mikhalchishina and Mikhail Nishidin, we construct a representation Phi-M from VBN into automorphism Fnn by the following rule, and we proved that any previous representation can be get from this representation Phi-M. And it's interesting to study the question about faithfulness of this representation. Oleg Sterenthal proved that the representation phi and b of the group VBN is not faithful for every n greater or equal 4. In fact, he proves that the element b, which has the following form, lies in the kernel of representation phi and b. And it's not difficult to prove that this element also lies in the kernel of all representation phi SW, phi BD, but this element does not live within the kernel of phi M. And I think that now this representation is more interesting. And using this representation by, sorry, using this representation, we construct a representation of multiple virtual braid group K and VBN. To do it, we defined the group Fn Kn. This is the free product of free group Fn and free abelian group of rank Kn. And the actions is defined by the following formula. You can see that image sigma I acts as in Artin representation. On the out generators, he acts as permutation. And here we have some conjugation with this element. And we prove the following theory. The map Phi-n, Phi-k, which we define on the generators, in fact define a representation of a group multiple virtual braid group, and also symmetric multiple virtual braid group in automorphism of this group. And as corollary, we get that this representation is not faithful for all n greater than 2 and k more than 1, because Km VBN with tilde is the non-trivial inversion of the group KMVBN. But of course, the question about faithfulness of these representations is open. And now I am going to a not invariant. As in the classical case, we uh, have a map from Braid to the link using the operation of closure. We can use this operation for virtual, for a multi-virtual Braid group, for braids, and we get a correspondence links or not. For example, if L is the set of classical link in R3, then the group GL of link has the natural definition, its fundamental group of complement L in free sphere. And Artin proved in free space. And Artin proved that if L is isotopic to closure of some braid beta, where beta lies in Bn, when this group has the following presentation. It's generated by element x, x1, xn, and has the following relation. Xi is equal to image of xi under the action of this automorphism. And now we can give the more general approach. Suppose that we have an algebraic system with a set of generators and defining correlation. For example, we have a module, group, quandle, biquandle, and so on. And also suppose that we have representation of multiple virtual braid group into the group of automorphism of our algebraic system. When we can construct an algebraic system of the following form, A with index phi of beta is the algebraic system which is generated by element of this type, where and defined by the relations R and defined by the following correlations, which acts from the action of automorphism phi beta. This algebraic system is an invariant of the virtual link if image of braid is either morphic to the image of beta prime for each pair beta prime and beta which are equivalent. Of course, to prove that it's invariant, we can use Markov theorem or Reidemeister moves. For example, in the case of virtual braid group, we proved that the map phi m from VBN into automorphism F and N is defined an invariant of virtual link or virtual braid. And of course, we can use the similar approach for multi-virtual braids, braids not. And now I want to say about some question of Professor Kaufman. Now let us consider two virtual link diagram. It's a diagram on the plane with three type of crossing: classical crossing, crossings of this type and two type of virtual crossing. I will denote one type of virtual crossing by circle and the circle by square. And of course, as usual, two virtual link is equivalent class of two virtual link diagram by the generalizes Reidemeister moves. We have the natural definition. And for example, if we consider hoop link with two virtual crossing of one type virtual crossing, when this hoop link is trivial and it's equivalent to disjoint union of two circles. But on the other side, if we have hoop link with two different virtual crossing, then it's not equivalent to the trivial link. And Kaufman formulated the following question: is it true that any single component diagram decorated only with two virtual crossing, reduced to data by data move to a circle. It means that is it true that any two virtual node with only virtual type of crossing, it's equivalent to a trivial node. And here it's illustration. If we have a hop link with one type of crossing, it's equivalent to the trivial link. But if we have a hop link with two different type of virtual crossing, it's non-trivial. And the main result of our last part, it's the following. There are two virtual nodes with only virtual crossing, which are not equivalent to the trivial. Hence, we have a negative answer to the question of Professor Kaufman. And the idea of the proof is the following. We know that Kishina node is a non-trivial node, but it's connected sum of two trivial nodes. And we know a lot of different proofs for this fact. But for us are interesting the following result. This result, it's says that if we consider flat Kishina node, flat means that we have two type. We have virtual crossing and flat crossing, when this flat Kishina node is also non-trivial. Kaufman and Manturov proved this result, and way to do it, they construct so-called virtual bike bundle. Virtual bike bundle is some generalization of classical bundle. And from this bundle, they proved that it's not equivalent to a trivial bundle. And using this bike bundle, we can define a free module M over some ring and define two switch. Switch is the map from the M times M to M times M's. And using this map, we can construct a representation of flat virtual braid group into automorphism of this module. And we use this automorphism. We can construct virtual bike bundle for any braid, which is invariant of a flat virtual link. On the other side, we have a homomorphism from two multiple virtual braid group into the flat virtual braid group. Under this map, sigma I goes to Ti and rho I goes to rho I. And we have flat virtual link. And this bike bundle, in fact, is invariant not only for flat virtual node, but it invariant of two virtual nodes. And at the end, I want to formulate the following question. Kaufman proved that the classical node theory embeds in a multiple virtual node theory. But is it true that virtual node theory or flat virtual node theory embeds into the multiple virtual node theory? We know that for a group it's true, but I don't know is it true for correspondence node theory. That's all. Thank you for your attention.
Thank you very much for interesting talk. Firstly, let